Welcome to this explainer. You know how AI learns today, right? It's basically a massive black box. Well, today we are exploring a truly monumental shift. We're talking about moving away from simply tweaking hidden opaque neural weights and moving toward maintaining dynamic, explicit software structures. It's a completely new architecture that allows AI to absorb feedback, preserve its capabilities, and actually evolve over time, all while remaining highly testable. Here is our roadmap for today. We'll start with going beyond the weight update, then look at fixing catastrophic forgetting, dive into the energy flow machine, master complexity and control, and finally, explore the new intelligence ecology. All right, part one, beyond the weight update. For over a decade now, the dominant learning paradigm has basically been all about data, loss, gradients, and parameter updates. You show a model data, it figures out how wrong it is, and it adjusts its internal weights. Now, this creates incredibly powerful systems, no doubt about it, but it also concentrates all that knowledge inside a really dense, opaque substrate. When the system learns something new, that feedback completely vanishes into hidden parameters. Contrast that with heuristic learning. Here, instead of burying every new skill inside neural weights, a code-writing agent maintains an explicit software system. The feedback energy doesn't just disappear. It gets converted into explicit, inspectable software artifacts. We're talking rules, logs, tests, and configurations that can actually be debugged and edited. Which brings us to section 2, fixing catastrophic forgetting. We've all seen it happen, so why exactly do neural networks forget? Usually, people just talk about catastrophic forgetting as a defect or a glitch, but the energetic paradigm frames this beautifully. It is fundamentally an energy storage and overwrite problem. Think about it. When you have a ton of different capabilities sharing the exact same parameter space, learning a new task pushes on those exact same parameters. The system has zero natural boundaries between learning the new thing and protecting the old structure. So what happens? The new learning literally just overwrites the old learning. So how does heuristic learning fix this? By totally changing the storage medium. Instead of sharing that one crowded space, old capabilities are preserved explicitly. Successful behaviors become concrete rules. Boundaries are set up to isolate one skill from another. Failed paths become actual failure detectors. And crucially, we get regression tests and rollback points. Now, explicit systems don't magically cure forgetting forever, but they make forgetting visible and engineerable. If a new update breaks an old scenario, you see it instantly on a dashboard, rather than just dealing with silent, hidden damage inside the weights. Moving on to part 3, the energy flow machine. Think of a heuristic system as literally an energy flow machine. You've got feedback coming in from a source, like test failures or system logs, and that creates a pressure or a gradient to improve. But the real magic trick here is the converter. This is the code-writing agent that transforms that raw operational feedback into maintainable code. That code goes into storage, which is managed by control points like regression dates. And just like neural networks experience loss, heuristic systems face their own kind of loss through rule bloat or overfitting to narrow tests. Fixing that requires compression, which means refactoring and consolidating those rules. This leads us right into the central causal chain of the whole paper. It's a gorgeous process. Feedback becomes diagnosis. Diagnosis becomes code and tests. Code preserves the behavior. Memory stores the lessons. Compression restores simplicity. And control keeps the system evolvable. The absolute lifeblood of this continuous improvement engine is a relentless two-part cycle, constantly absorbing feedback and then relentlessly compressing that history. Now here is the ultimate stability condition you absolutely have to remember. Feedback absorption without structural compression produces a code swamp. If you don't compress, you end up with tangled tests, a bloated rule base, stale memory, and skyrocketing maintenance costs. Every single local repair just sits there as an isolated exception. The deeper goal here isn't just fixing bugs, it is evolvability. It's knowing exactly when to add a rule, when to create a new module, when to consolidate exceptions, delete memory, or even freeze the system entirely. Section 4, mastering complexity and control. You might think the ceiling of a software system is just how many lines of code it has. Actually, scratch that. Line count is completely irrelevant. A clean 500-line system is infinitely easier to manage than a tangled 80-line one. The real burden is coupling complexity. That's a measure of how many interacting constraints an update has to respect all at once. We're talking state, rules, safety conditions, and timing, all tangled together. There are only two ways to raise this maintenance ceiling. You either strengthen the agent or you lower the architectural burden. And here's the hard truth. Better, smarter agents literally cannot rescue a badly structured system. You have to lower the architectural burden. And that is exactly why control in this paradigm isn't just some flimsy wrapper you slap on at the end. It's baked directly into the learning loop. Behavioral control protects your old capabilities. Interface control stops local changes from causing global corruption, and memory control actively roots out misleading lessons. High-risk updates actually require simulations, explicit safety constraints physically block dangerous actions, and compression control forces periodic refactoring. Learning, control, and memory all act together as one unified system. Now you're probably thinking, wait a minute, didn't we try rule-based expert systems back in the 80s? We sure did, and they failed because humans simply could not maintain them at scale. Every new exception invited another exception, until the human maintainers were literally too terrified to delete old code. But today, the new maintenance economy changes the cost curve entirely. Code-writing agents automate the search, the testing, the logging, version comparison, patching, and the refactoring. The bottleneck has completely moved from manual human labor to system architecture. To be completely fair and impartial here, explicit code does not automatically mean correct code. You've got real decay risks, local patches can accumulate without any conceptual consolidation, interfaces can drift, and the system might just learn to game your tests rather than actually solving the problem. Old memories might start polluting current decision-making. This is exactly why explicit architecture requires the energetic paradigm, bringing extreme structural discipline, constraint management, and failure memory to the table to prevent that decay. You can't just trust it blindly just because you can read the code. Finally, Section 5, the new intelligence ecology. So where does heuristic learning actually shine brightest? It's an absolute powerhouse in domains that are testable, feedback-rich, and where solutions can be represented in code. Think robotics control, complex system diagnostics, or continuous integration workflows. The structural advantages are huge. You get real interpretability because a rule written in code can be audited and criticized. You get insane sample efficiency, where one single patch instantly upgrades an entire strategy. And you get executable constraints. For anyone building AI that touches the real world, this means you finally have a system you can actually trust and debug. Let me make one thing crystal clear, though. Heuristic learning is not here to kill off neural networks. No way. Neural nets are still essential for perception and high-dimensional pattern recognition. What this paper is really advocating for is an architectural division of labor. Layer 1 uses neural perception to turn messy real-world data into structured signals. Layer 2 applies heuristic operational logic to run the explicit behaviors and constraints. And Layer 3 features agentic repair, where code-writing agents step in to update rules and compress history. The energetic paradigm is what governs this entire stack. We've seen recently that AI problems get way easier when you can verify the output, right? Like checking code or doing math. Well, heuristic learning adds a second golden rule. Problems become easier when they can be continuously iterated. Verification acts as your local truth. Iteration gives you forward movement. Memory provides continuity. Compression ensures stability, and control establishes the boundary. Woven together, they create a continuous living software process, rather than just a monolithic one-time model update. Real intelligence isn't just a one-off output. It is the ability to adapt continuously without breaking down. It has to convert feedback into structure, knowing exactly when to patch, when to refactor, and when to freeze. The next unit of intelligence may not be a larger model, but a better maintained intelligence ecology. If the entire future of AI relies on maintenance rather than just brute force scaling, we have to ask ourselves, are we building the right tools to govern this new ecology?